Okay, hello everyone. Let me continue on the photoablation part from the last class. This photo shows the surface of the, let's see, the cornea when using the laser. MD6305 has a 1053 nanometers. However, when you are making second harmonic, then the laser will become 526, and then the fourth harmonic will be 263 nanometers. And you can see that even though the energy from the photoablation is 20 microjoule compared with the 153 microjoule here, the surface is very smooth and clean from the 263 nanometers because this one is using the interaction mechanisms of the photoablation. However, 526.5 nanometer is using called as plasma-induced ablation, which is very different mechanism for the ablating the tissue. So here, as you can see, it is going to be very important to do the any kind of cornea shaping, which is the LASIK or LASIK, by using the laser. In that case, you have to use the photoablation interaction, which is using that short wavelength. The modeling of the photoablation can be done by following Lambert's law. So in the Lambert's law, it describes the intensity at the depth of Z is going to be intensity at the surface of the tissue, and then the exponential decay function, the following the attrition coefficient alpha and the depth of Z. And this photoablation is not going to occur in any time, but only when the light intensity at the depth of Z is larger than the certain threshold, which is the IPH. So therefore, in the depth of the Z, the light intensity I0 exponential minus alpha Z should be larger than the threshold level. So when you want to estimate what will be the ablation depth, D, then D must be same as the threshold level for the intensity. So from this equation, it can be estimated by following this ratio between a light intensity at the surface and the light intensity for the threshold for the photoablation. So by using this one, you can easily estimate what will be the depth when you are using the laser for the ablation. But this is going to work between the threshold of the photoablation and between until the threshold for the plasma generation. So between that, it works well. However, below or higher than the plasma-induced plasma generation threshold, this simple model doesn't work well. So ablation depth per pulse is going to be a function of instant energy density, which is E sub 0. And the E sub 0 is going to be light intensity at the surface, and then multiply with the tau, which is the tau is the pulse duration time. So if you look at the ablation curve of the rabbit cornea, then it can be seen in this figure 3.36. As you see the increase of the energy density on the x-axis, the ablation depth is also increased. And the ablation depth here is shown as a micrometer per pulse. And then between those curve, which is kind of following sigmoidal curve, we can find the kind of linear relationship in the middle of that. And then for that reason, the depth of D, ablation depth D can be estimated very well with this following equation. However, below this lower energy density level or higher than some certain high energy density level, it does not follow the same equation but it is much, much slower. So getting approach to the zero, the let's say the threshold for the photoablation is going to be very similar to the I sub zero. So the IPH, which is threshold for the photoablation, is not actually very sharp. And then that is because of the inhomogeneous fragment size of the molecule. So some are big and some are small, so that the IPH, the threshold for the photoablation, is not actually uniform, but it has a wide range of that. And then the ablated fragment size is increasing, then that causes the decrease of the threshold of the photoablation, because we know that when the volume is increasing, the surface area is getting smaller. So with the same volume, to make a bigger surface area, you need to make a small volume, but many of that volume, the sphere. Then the overall surface area is going to be larger, which can be seen from here. So area can be coming from the 4 pi multiplied with the radius square, but the volume is 4 over 3 pi and r cube. So when you have a smaller volume, then in fact, the surface area can be increased relatively. So this ablation curve of the rabbit cornea, which you have seen here, so lower part is because of that, and then but higher energy density area, this is also not following this simple linear equation. Above this IPL, PL means the plasma, and the IPL means a threshold for the plasma generation. So in the next class, you will see the optical breakdown, and the optical breakdown is happening when there is a very high intensity of the light is focused in the very small volume. So, but to make the plasma generation, there is also some threshold of the light intensity. So beyond that plasma-induced ablation threshold, then the plasma shielding phenomena is happening, which can be actually seen in the next slide. So what is the plasma shielding phenomena? So as the name says, the plasma shielding means that when the high intensity focused light generates the plasma, and then the plasma itself is going to actually observe the following the light to the same place, so that it is actually protecting the same region by absorbing the more laser energy. So that the name is plasma shielding phenomena. So when there is a high electric field, then you will have a high power density. And then this is going to be the condition to initiate the plasma. And then once the plasma is generated, then the plasma is going to observe the succeeding laser radiation energy. And when they are observing energy, you can easily imagine that the heat will be also generated, so that it will cause the additional thermal effects. So alpha PL is a plasma absorption coefficient, or mu sub A in PL, which I guess in here, alpha sub PL is more simpler symbol. So this plasma absorption coefficient, alpha sub PL, is much greater than the alpha, which is the tissue absorption value. So compared with the tissue absorption, this plasma absorption is much greater. so that it can absorb a lot more energy from the succeeding laser irradiation to the same spot. So all of this huge energy is going to be dissipated to heat, and then the laser energy coming cannot contribute to the further increase in the ablation depth, so that this ablation curve is going to be saturated. So in the 1980s, there has been a controversy of whether photoablation belongs to photochemical or photothermal interaction. And then the researcher concluded that photoablation is its own interaction mechanism. So photoablation is also called as an ablative photodecomposition. And then, but you also have seen thermal interaction also causes the ablating the tissue. So let's look at the difference between those two. So photoablation has to have enough energy from the ground state of the AB molecule to the excited states of the AB molecule, which is shown here as AB star. So by turning this ground state AB into the excited state AB star, as you can see, the energy is going to be much higher. And then to lower this energy, what they have to do is basically they need to make a much longer separation between A and B. And then there is basically repulsive state. By having that repulsive energy force, then they will be separated. So the AB will become A and B, and then boom, and going away. So, however, thermal interaction is different. For the thermal interaction, the laser is providing just enough energy to move to the high vibration energy, either within the ground state or to the low electronic state, including any of its vibrational states, so that it actually causes the vibration, which can be a kind of simply friction, and then it will generate the heat. So between photoablation and the thermal interaction, the key difference is the photon energy irradiating tissues. So only if when the light has an energy of the greater than 3.6 electron voltage, which is corresponding to the wavelength for the shorter than 350 nanometers, then that allows the single photon can dissociate the carbon to carbon single bonds. Otherwise, the thermal decomposition will happen. So for the photoablation, it is very important to choose the right wavelength. And then multiphotons of lower than 3.6 electron voltage can be actually added up in energy. And then that may lead to a dissociated state too. However, during the time needed for such a multiphoton absorption process, other tissue areas are also going to become vibrationally excited, so that it will lead to a global increase in temperature. And then they will cause some observable thermal effects, which is either vaporization or melting. And then if that process is associated with the ablation, then it is called as a thermal decomposition. There are exceptions. Even visible or infrared laser can also interact non-thermally if the pulse duration is shorter than the 100 picosecond, and pulse energy is high enough to induce localized microplasma. which is actually meaning about the telling about the plasma-induced ablation, which is coming for the next class. So this figure shows the relationship between the photon fluence, which is here as energy per area, with the thermal components, which is the energy per area also. So for the 308 nanometer, you can see it is kind of linear relationship. But when you have a shorter and shorter wavelength, then you can see that the thermal component from the light energy is much, much lower. And then when you are using 193 nanometer, you can see even if you increase the light, the photon fluence, but thermal component is going to be very minimum. However, I guess you also heard about the toxicity for the ultraviolet range, the light. So the ultraviolet, which is UV light, is actually having very high power so that it can actually cause the photoablation, which means that dissociating the molecules in the tissue by providing enough energy to break down the bond between the molecule and molecule. So that when the UV light is coming, it can also cause the damage to the tissue. And then they can directly damage the DNA. And then in the DNA, you can see there are TA and then CG are binding each other. And then between those TA and the C and G, there are the hydrogen bonding to each other. But those hydrogen bonding can be breakdown by illuminating the UV light. This is the Gattaca, which is the title of the movie. I don't know whether you have seen this or not, but it's a very interesting movie that looking at the DNA information, so that by looking at the DNA information, that person's future is already decided. So what kind of job that person has to do, is going to be totally depending on the DNA information. So when you have time, this is old movie, but it's interesting to watch. So DNA is strongly absorbing UV light, especially in the 240 to 260 nanometers. For the UV absorption to the DNA, they will actually disrupt nucleic materials of the double helix strands. And then it can form a dimer from two adjacent pyrimidine bases, which is TT and CC. And then this can be either repairable or unrepairable. So our body has a very kind of natural the repair mechanism. So if something happened, then it can actually fix by itself. However, some cases it can't. And those unrepairable damage is going to initiate mutagenesis, which can be a cancer cell for the later. So here you can see there are the T and T, and when there is ultraviolet light, it can cause the thymine dimer. So the T and T actually bind together here. They are supposed to be not binding each other, but because of the UV light, it can bind together and then making thymine dimer. When this happens, you can see T should be connected with A. However, now T and T are connected to each other so that it can make the kink in the helix structure. This slide shows the UV damage depending on the wavelength. So the laser for the 193 nanometer, and then mercury lamp can generate 254 and the 308 like that. But this krypton fluoride laser 248 nanometer is not used in the medical applications. But by using this one, you can see the high power mercury lamp, low power mercury lamp. This um, Between those high power versus low power, there are differences in terms of this UV range, the light. So for the low power mercury lamp is in general uh, generating 253 nanometer the light, but the other a high power mercury lamp is generating a wide range of the light in the UV. And then this bottom graph is showing the surviving fraction for the ovary cell of the Chinese hamster. As you are increasing energy density, then of course those cells will die. So surviving fraction is less than like 2% or 3% as they are increasing.